think you can get obviously just I think it's
So these are identical. Okay.
view.
Okay. Oof,
Right, how you
that was
doing?
close.
How you
Yeah.
doing?
I'm okay. Now, everybody who's after my own heart, that is to say, people call me late, I had a chance to get it. I in fact didn't have any problem with my mouse. This was just to allow me to
That's
start
right.
late and thus honor
Perfect.
the latecomers. Okay,
Excellent, thanks very much, guys.
thank you. Well, maybe just stay just. Okay, just stay.
Yeah,
just-
but the thing is, I'm a bit worried about the wires. We had too many wires there yesterday. Can we just leave it there?
I'm just standing here.
All right, I'll move it.
That's what the microphone is. It's picking up.
Oh, I see. Ah.
It's facing completely away now.
You want like that?
It's still facing away, but at least it's close.
Facing away. Where's the mic? Is the mic in here?
Yeah, right there with the camera.
Oh, okay.
Hello, can everyone hear me? Everything's okay? All right, so just stay till I change the first slide. Okay, so I'm going to tell you about mean flows and frequency prediction. Okay, so everybody knows the cylinder wake, right? Everybody knows and loves the cylinder wake. Here on the left, we have the ideal flow. Around the cylinder, the flow is coming from the left. On the right, we have viscous flow, and it has its, everybody knows the feature of it having a recirculation zone, and that's used as a test to see when your code is good, to see if your circuit is the right place. These are great pictures. The one on the left is a laboratory experiment. The one on the right is from way up high above the clouds, and it is the wake of not a cylinder, but a mountain, which is up to the top left. And the mountain is not tall enough to pierce the clouds. This is a great illustration of the Taylor-Proudman theorem. It's used, its best use is to show that. Anybody want to know about that? Taylor-Proudman?
Yes.
Yes, okay, Taylor-Proudman. Flow in a rotating, sufficiently rapid rotation, the flow is the same at each plane. Can people see my hands or not really? No, it doesn't depend on the vertical coordinate. Okay, so supposing you have a mountain here, and naturally down here, the flow has to go around the mountain, right? Because the mountain's here. But if you go up here, there is no mountain. But the flow has to be the same on top as on the bottom. So it's going around a virtual mountain up there. Isn't that amazing? And you see an illustration of that. The mountain, there is no mountain piercing the clouds, but it's as if there was a cylinder, as there is in the leftmost picture. And this is the wake of the virtual mountain. And I think is this a movie? Yes, it is a movie. So here is the flow past the cylinder. The colors are vorticity, and you see this is very characteristic. It's one of the basic dynamical problems. It's after a certain Reynolds number of 46, it starts to emit these vortex, von Karman. It's called von Karman Street. It's also called Baynard. It's the great pioneers, our great ancestors found this. Okay, so everybody see that, and you see that it has a frequency. Red, 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 right? Okay, so the talk is about that. And that question is considered so basic and important that here's a paper by Charles Williamson, who did a lot of work, experimental work on the cylinder wake. And what he's plotting is the non-dimensional frequency, the one I just said, red, red. FD over U infinity D is the diameter of the cylinder. U infinity is the flow coming in from the left as a function of Reynolds number. And this is the key figure on his paper. It's from '88, so a lot has happened since, but at the time, it's the key figure. And what is it? This is those dots are his experimental points, the frequency, and the line, the curve, is a completely empirical fit, some kind of function that he just made up. And it was considered so important to know the frequency as a function of Reynolds number that they published a paper with purely an empirical fit to that. You're going to tell me that's not so, maybe, or?
Well, why is there such a gap between data? Is that artificially displaced?
I believe it's artificially displaced, yes. I think so. Better check that, yeah, before I present that another time.
It's not a constant now.
Yes, yes, I know what he's saying. Why is there a constant there?
It's not a constant. You think it's this way? No, I mean, it's clearly more.
Right, the vertical is not uniform.
Yeah.
The gap is not uniform.
Anyway, then there's the transition to 3D where all bets are off.
There's good correspondence at the bottom there, and then there's a gap.
This one here, this gap. Here he's talking about.
I think it's just a line he drew on the graph.
Well, it's Trump has been there with his shirt.
6-year-old.
Okay, we'll fix that. That wasn't supposed to be the point of the slide. The point was supposed to be it's considered important to forget that frequency. Okay, so here is a paper by Dwight in 2006. And this is the base flow. That is, you saw an example of it over here, the base flow, and you see this recirculation zone. This is going to be important here. So this is the base flow. Hold on, okay. This is the base flow, Reynolds number 40, and it's stable then. Remember, I told you that the instability happens at Reynolds number 46. So you can see that at Reynolds number 100, it is no longer this. You don't get this in numerical simulations. You can, however, get it if you freeze, the symmetry across this plane, then you can get this, compute this unstable basic flow, or you can get it by Newton's method or something. But of course, what you do get if you do numerical simulation is the cylinder weight, the one we just saw. And this is at Reynolds number 100. So you've just seen that blue and red, here's black and white. And you can take its mean in time over one period. And this is what you get here. And you'll notice that this is at Reynolds number 100 when there is when the flow is unsteady, the natural one. And you see that the basic flow at Reynolds number 100 is not the same as the mean of the cylinder weight. Okay, so that's really kind of one of the important things here. And anybody have any questions so far? No, you sure? Okay, I like to. There'd be a lot of questions. Okay, so all right, it's
I've got a
not.
question for you.
Yes.
Can you point to these images with your mouse?
Yes.
I can't see your mouse.
Oh, really? It doesn't. Oh, that's too bad. That's what I wanted it to be. I didn't want to be in the display mode.
There is
Okay.
a point. There is a pointer. There's an old-fashioned wood.
So now I have to master all these
Well, if
different
you want
tools.
to, I don't know.
But yes, no, that's fine. I'll use the, so I have a mouse, old-fashioned stick. I'll chase the mouse with the stick. Okay, so anyway, this thing here, this mean at 100 is not the same as the unstable basic. Okay, well, maybe no surprise. Let's do some equations. First equations of the talk. Here we have the basic flow. And then we have a temporally periodic, this would be a steady state, like the one that's unstable or stable. The temporally periodic rate flow, just Navier-Stokes. Let's define a capital U, capital U bar as the time average over a period. And now let's do the usual thing we do. Let's linearize about the steady base flow. And that is how in the steady base flow, like this one or this one, that's how we get Hopf bifurcation. We get, okay, everybody knows linear stability analysis, right? We would then put sigma here and we get sigma as a function of Reynolds number. And when it crosses 0, that's okay. But now let's do something else where we linearize, instead of linearizing about basic steady flow, we're going to linearize about the temporal mean. Okay, so this is strange. I mean, we see the symbols, they're just these symbols, except with a U bar over it. Strange and unjustified procedure, but it's very successful. And let me show you how successful it is. This is frequency as a function of Reynolds number. No offset this time, Rich. There, things look good, right? Okay, so what is this? This is the Reynolds number, and this is the frequency. And the this is the linearization about the base flow. Okay, so this is where you get a Hopf bifurcation, and you can see that here. This is sigma, the growth rate, and you see at this place here, 46.
You can't see your mouse.
Oh, thank you. What a pain, what a pain. I knew I should. Well, anyway, okay. Sorry, so this is the growth rate sigma, so the eigenvalue is sigma plus I omega, and we see that this growth rate crosses 0 here. This is the Hopf bifurcation 46. At this place here, we have a frequency, which is the Hopf frequency, which is obtained by linearization about the base flow, and we also have the actual frequency computed by DNS, which is these triangles, yes, and the stars are the linearization about the mean flow. So we said this is a strange and unjustified procedure, but look how good it is. So we better find some justification somehow. I mean, one could be a coincidence, but 2, 3, all this matching. Any more questions? No? Nobody? Okay. So you see, this is bad, as we expect it to be. It should only match here at the Hopf point. And this is very, very, very good. Okay, so now let me, oh, and then there's another thing. There's another thing. When you can do this calculation about the base flow, you also get 0, excuse me, not the 0, not the base flow. The mean flow, you get 0 as the real part, as if it was marginally stable. You don't get that about the base flow, of course, because the eigenvalue becomes more and more unstable, bigger and bigger growth rate. But here it's 0. Those triangles are 0. What could this mean? So let me give you a name here, because I went around for a long time saying linearization about the mean flow gives you a real eigenvalue, which is 0, and an imaginary part, which matches the nonlinear frequency. And that is a long phrase. So one of my many achievements is to give it an acronym, RZIF, which stands for real, zero, imaginary frequency. Right? Okay. And the French put in acronyms for any old thing constantly. Anyone who knows French science knows. But this, I think, is not for anything, because I went around saying you get an eigenvalue whose real part is 0 and whose imaginary part is the nonlinear frequency many times before realizing we needed an acronym for this. Okay, so that's what RZIF is. Okay, RZIF is the fact that these triangles match this line and that these triangles are along 0. Got it? So now you know what RZIF is. Okay, let me give you some more pictures which make it all more convincing. This is still all from Dwight's paper from 2006, Europhysics Letters. This is just a trace as he's doing a simulation of, and so you see the oscillation, and this is the beginning from the base flow, and then you get to this, and you can, if your eyes are good, you will see that the frequency, the period here is longer than the period here. So indeed, it's oscillating at the Hopf omega, and it's getting to something which is the nonlinear frequency. And here is that same thing shown here in this picture. This is the original. This is the sigma from the. Well, anyway, you see, this is the frequency here at the that you get at the end, which is the right one over here. Now, this is an interesting thing. This is a phase portrait where you have a V at 2 different places, and the base flow is here. This is the unstable, steady cylinder wake here in black, as it's been since the beginning here and over here. And look what it does. If it were the Hopf bifurcation that's illustrated in your nonlinear dynamics textbooks, it would oscillate around this black thing, right? You would have you would have it go, right? But instead, you see that as it develops, it's leaving that, and it's going here, and it's oscillating about a center, which is not the same as the base flow.
It's on the y-axis there.
Here, this.
The middle one, okay.
Okay, so it's 2 different velocities at 2 points. Okay, so here's the mean flow. So you see it's oscillating about a different thing, which is, you know, what we're starting to realize. And okay, and we see just the tremendous interest that there is in this problem. This was Malkus, who Rich knows well and who we all know, and he said the temporal mean of a turbulent flow, this is not turbulent, should be marginally stable. And here we have we don't have a turbulent flow, we have this periodic flow, but we see it is marginally stable. It has a 0 frequency, 0 growth rate. So, you know, some ideas maybe of Malkus's. Here we have other people writing about wakes, just how important it is. This has been what Pierre, who interested exactly in the frequency selection of the vortex change. So a lot of people are interested in this question because the cylinder wake is a prototype. Right, Javier, right? Everybody who's senior here knows that. You've seen the cylinder wake a gazillion times. And then here's Bert Nowak, who has spent a lot of time working on models for cylinder wake. So question, when is RZIF satisfied and why is RZIF satisfied? Right, we said it was unjustified. We can do a little better than that, right? Okay, so let us do a different problem. This is thermosolidal convection. This is one of my favorites, and I'm going to take a little bit of an aside and tell you about thermosolidal convection because I like it so much. How many people know thermosolidal convection? How many people don't know thermosolidal convection? Oh, good. Okay, that will justify my little detour here. Okay, so this is very schematic. This is the easiest problem you can have that presents. This is two plates here. There's periodic boundary conditions on the horizontally, and there's free slip boundaries top and bottom. So you get to use trigonometric functions. And we took the lane to be exactly the critical one. And what we do is we're setting the temperature and the concentration. This is a mixture like water alcohol. We're setting the temperature and the concentration here and here at different values. So there's a thermal gradient and a concentration gradient. And that's what's driving it. And they could drive it in the same direction. You know, hot and cold mix, you do this. Whereas cold and hot is stable, or the concentration has the same thing, because we can remember now that what is convection? You might think, oh, temperature makes the fluid rise. The hot fluid rise. No, it is density that makes the fluid rise. It is density, and density depends on temperature. But we tend to just shortcut that and say, oh, hot fluid rises. No, light fluid rises. But there's more than one way to make a fluid light. You can make it warm, yes, but you can also have this concentration. If your water and alcohol have different concentrations, you will have different density. Okay, so in both cases, it's rho that is driving it. Anyway, you can set the two effects to be opposite one another. And oh, this is all just the non-dimensional parameters in the equations and stuff. Nobody wants to see that, right? No. Okay. So here's
Wait, can I see that?
Prandtl number, Lewis number, Rayleigh number.
Oh,
That's okay? Or no, but ask me, Sean, really.
No, I just want to see.
Yes.
You're calling it the Lewis number, yes.
Oh, but I have it wrong. I've learned this later.
It's
This
always-
is the opposite. This is the inverse Lewis number.
This is like Schmidt inverse Lewis.
No, I think not. I think Schmidt is yet another one, but this is the inverse of the Lewis number. I discovered this after I'd already published twice with the wrong definition. I think I may be wrong, but I think that maybe that Edgar Knobloch got it wrong and I got it wrong from him, but I'm not absolutely sure. I have to check that again.
Explain that here.
So yes, so here is Edgar Knobloch, and how many of you know Edgar Knobloch? Everybody knows Edgar Knobloch. Okay, so he, with his then graduate student Jim Swift, they did in the 1980s, the golden period of dynamical systems. They figured this out. This is when there's a Hopf bifurcation that breaks O2 symmetry. And what's O2 symmetry? It's just, you know, it's just what we had before. It's just you're periodic in this direction here in the X direction, and you're also reflection symmetric. Okay, and when you have a Hopf bifurcation that breaks that, then you produce periodic states. Naturally, it's a Hopf bifurcation, but you produce two branches of them. You produce standing waves and traveling waves, right? And the nonlinear dynamics tells you that you can only have those. You can't have 3/4 left traveling and 1/4 right traveling, which you could in a linear, but so again, good illustration of nonlinear dynamics. So you necessarily produce two branches there at the same bifurcation point. And as I'm just taking a little venture here because I like this so much. The thermosolidal conductor also produces steady states. This has nothing to do with the Knobloch thing. I mean, it does. He did some things like this later, but okay. With a saddle node. And look at this wonderful, wonderful thing. One of the branches, the standing waves, it ends by meeting this unstable steady state. And the other one, it meets it by at a homoclinic bifurcation. I think it is. And the other one ends by meeting the other piece of the saddle node at the travel, and that is at a drift bifurcation. Okay, so don't tell me that's not wonderful. This is, I think this all nonlinear dynamics classes should have this as the basic problem. It illustrates all the phenomena. So here's the drift pitchfork where it's terminating the traveling waves, and here is the heteroclinic, which is terminating the standing waves. And I did a complete classification of all this in 2001. Okay, but now let's get back to RZIF and SCM. What we're talking about here is this Hopf bifurcation here, a Hopf bifurcation. This one here, okay? The fact that it ends on these steady states has nothing to do with the main story. Okay, so let's get back then, and here are traveling waves and standing waves produced by numerical simulation. So the traveling wave travels, the standing wave stands. Right, everybody happy with these movies? Okay, and
Does
now,
the amplitude grow?
I'm sorry, say again.
Is the amplitude growing?
Well, this here, yes, because this is a simulation starting from a small amplitude, but you know, eventually it reaches an amplitude that's stationary. These are perfectly ordinary limit cycles. There's nothing special. The only thing.
These are two solutions from your previous diagram.
That's right. And actually, one of them is unstable, but you can use standing waves, it turns out, are unstable, but you can get it by freezing the symmetry in the middle, say. And it's also only weakly unstable, so you can get it actually for a long time before returning to travel. But yes, these are solutions to the previous equations for one parameter value, same parameter. And these are isotherms, I should have said. Red, those two, right? Everybody realize
So
that?
there's two solutions on the same vertical line.
That's right. Two solutions, same vertical
Can you
line.
point to the previous diagram?
Here, say, and here.
Also, they're both on.
No,
Oh,
they're
that's
only
fine.
drawn that way to show, okay, here I was using the dash to show a periodic rather than a steady state. Okay, there aren't enough symbols, as we know.
So you plotted density here,
I'm plotting, yeah, temperature. Or
but
density.
then what happened to salinity?
Yes, there's that too. You're right. I believe it's density. But I'm not too sure because I study these but only in a very mathematical way. I think you would have more understanding about what I said that very fast. All its points. But
Yes, indeed, there is a question. So is it heated from below? Is it or is it the real salinity temperature?
this is not survey effect. This is both concentration and temperature imposed. If that's the
Both
question.
unstable.
Hold on just a second.
Because we have
No,
stability
absolutely.
of a different.
No, that's right. I'm sorry, hold on just a second. The no, they're unstable, only one of them is unstable.
But then you can get the same gradient in many different ways. So like, that's what I'm asking.
Oh, yes, you have a good question. Here I thought I would just take this little,
There is a very interesting physics.
Yeah, double diffusive stuff.
Double diffusive.
that's right, I know that here are the words, double diffusive, binary fluid convection. There's also something called salt finger. And thermosalinity is one variety of these problems, but they're all have to do with concentration and temperature fighting it out. That is right, even if I'm not. But it's true, I can do with a little more physical understanding and maybe I'll get that. Okay, so here's stills of the traveling wave. This is just 4 times. You can see it's a traveling wave. The mean flow, because we're going to get back to actually linearizing about the mean flow, looks like this. Since it's a traveling wave, naturally it's independent of x, just as it's independent of time. The temporal mean is a spatial mean. Okay, the mean flow looks like this. And now you see, lo and behold, this is omega, the frequency, and sigma, the growth rate of linearizing about the mean flow. And so the exact frequency, the one you just saw in the movie, it matches the omega that comes out from the linearization eigenvalue problem, linearizing about the mean flow. If you linearize about the base flow, the conductive state, you don't get anything like that frequency. So it's a lot like the cylinder wake, right? I mean, they agree at the moment of bifurcation, they have to, but they don't anymore. And if you look at the sigma, the growth rate, well, it's 0 when you linearize about the mean. So again, you have marginal stability. So that's great here. And of course, the sigma from linearizing about the base flow hits 0 and becomes positive after the Haber bifurcation, as it must. Okay, good, right? Everybody happy? So we have another case. It's not just a cylinder wake, because this whole thing has been studied very heavily for the cylinder wake and hardly any time for at all for these things. Now we go to the standing waves. And so you see these are nice pictures of 4 different instances of the standing waves. The mean now no longer is X independent because you have these nodal lines right here. Mean is no longer X independent. Let's linearize, but it is time independent. We can linearize about it. We linearize about it. And look, here is the linearization about the mean. And here's the linearization, here is the exact frequency. So they're no longer the same. In fact, you would say that the exact one matches the one from linearizing about the base flow, the conductive state, better. In the beginning, anyway, it's tangent, it's really nice. Now this one though, it's true that this one goes up straight and this one shows the same tendencies, which I think is interesting, and I haven't understood it, but I think it makes sense. It shows something here. And the same thing here for sigma. So here we showed that we don't have if. We don't have the imaginary frequency. And here I show you, you don't have RZIF, you don't have RZIF. You do not have that the real part, the linearization about the mean, is 0. It's not marginally stable. Aha, and this is the same parameter value. So this is important because up till now, people had been saying, oh, so I wonder, maybe I can prove that that you have the match the free, maybe I can prove this RZIF property. Well, you better not be able to prove this RZIF property because here is a counterexample. Right? And I believe it was, everybody was all just trying to prove it. So it's not so. It's
But it was approximately, wasn't it?
approximate. It was unjustified.
No, yeah,
Right. And it was, yes.
okay, but in this case, the mean is unstable.
This is true, but I actually don't think it has anything to do with that. Although that's Portman also said that, but we will discuss it in just a moment. Come see, you will see the further elements that I have. Okay, so here this just repeating it, that the traveling waves have the RZIF property, meaning the black and the red curves match, and the standing waves do not have the RZIF property, meaning that the red and black curves do not match. And now you might want to see these things here because they could shed light. This is what we saw before, but the same kind of thing that Dwight did for the cylinder, but now done for the thermosolidal. The same thing. Here is the base flow plotted here, and here is as it evolves in time, it goes here and it now oscillates, yes, but about a mean flow, which is elsewhere. That's for the traveling waves. For the standing waves, if you do the same kind of thing, it's not certainly not as straightforward a picture, right? It's doing this is the base flow, this is the mean flow, and it makes a bunch of adventures in this. Yes,
Your mean is X dependent.
it is.
Did you try to have X average?
I did not. It's true. Just hearing you say that, I knew this. That's a good question. I wonder if it would give the same. Yeah, that's a good question. True. What results would it give? Okay, so now let's give some explanation, or at least part of an explanation. Let's just write some exact things. Evolution equation, right? Let's do a temporal Fourier decomposition. This is completely straightforward. This is 0, and then this is 1, 2, 3, 4, the harmonics. Let's substitute the Fourier decomposition into the evolution equation. Here's the equation satisfied by the 0 mode. So you have 0, and then this says 0 plus 0 equals 0. And this says, say, 3 minus 3 is 0, and 5 minus 5 is 0, and so on, right? So these are the ones that contribute to the 0, right? And then for the first component, say, either the I omega t, You have I omega, you have the L from here, then you have 0 plus 1 equals 1, 1 plus 0 equals 1, then you have 2 minus 1 is 1, you have 1 minus 1 plus 2 is 1, then if I continue this dot, 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 you'd have 3 minus 2, 4 minus 3, you know, etc. Right? Okay. And I'm going to call this stuff here N1. Yes.
You want to draw the base.
Exactly. That's right. Exactly. That's exactly. Now that's not quite what I had expected here. Yeah. Okay. This is what I want. Right. Exactly. So as you said, I want to drop this, and lo and behold, what I get is that this equation is exactly the linear one. So there's not some mystery eigenvalue. This and that. This is merely the governing equations. Plug in the Fourier series and truncate. That's all. Okay. So that's good. And now here's some justification. Let's suppose that the temporal components behave like this, and that's often the case. They decrease, you know, as the harmonic degree goes up. Then we have an epsilon from the 1, and this is order 0 because it's the bar, epsilon from the 1. And here we have 3. Why do we have 3? Because 2 plus 1 is 3, and so on. Okay, whereas here we have 0 plus 1 is 1. Now you might think that would work for all of them, but it doesn't. The other ones say this one, this is, or they're the same order. 2 plus 0 is 2, 2 plus 0 is 2, and here the N2 starts off with 1 plus 1 equals 2. Yes.
So if we go back to the Kalman vortex tree,
Yes.
there is no epsilon there. The mean flow is differing from the street in a big way.
Yes. Yes. Quite right. That's right. I'm just writing stuff. That's absolutely right. Yeah. Okay. And here so I'm saying that this thing here of dropping the N1 does not apply to the other ones. It does not apply to dropping the N2, dropping the N3. It just applies to dropping the N1. And as we said, you know, if the N1 can be dropped, then we have the RZIF property. Okay. But why would we have this? Is it true that we have this big separation here where we can drop the N1? Do traveling waves have a highly peaked temporal spectrum and standing waves don't? Well, yes, fortunately. Here we go. We have, this is now the spectrum in N, and you see that the 1 is much bigger than the 2, or rather the 2 is much smaller than the 1. For the traveling waves, and not so much for the standing waves. This is at a particular Rayleigh number here, reduced Rayleigh number. This, if we take the ratio of this to this for all the Rayleigh numbers, we see this continues to be the case. There's a factor of the standing waves is not very different, and for the traveling waves, it is. Okay, so we've kind of explained it.
Can I just ask, what's that top red dots? How did you get to that?
Yeah. How? Yeah. What are those things? Oh, U2 over U0. So that is.
Oh, you divided by U0.
Yeah, divided by U0. I too was wondering about what I was doing here. So it's this ratio. Yes. It's this to this. Yeah. There was a reason for that, why it couldn't be dividing by U1 because you're normalizing twice or something. I don't remember why, but yes, thank you. Okay, so great. So now we understand it. Pretty much, although it just pushes the question further back, which is when do you get highly peaked spectrum and when don't you? And I have an explanation for the thermosolidal case, but which doesn't work for the cylinder weight case. And I skipped that, and I guess given the time, I will continue to skip that. But it pushes into that question. When do you get highly peaked spectrum? Okay, so now remember I had another initial in my title. I said RZIF and SCM, so you know RZIF. Now let's go to SCM. You noticed that we used U bar freely in everything that we said, as if we had U bar. maybe numerically or something. But so this is not a shortcut for calculating anything. You can't calculate and you have to get the U bar. You have to do a full simulation. So here, let me skip this other stuff here. So some other people, this is François Galler's group, Vladislav Montelugo and Cristobal Ariata. They published the PRL in 2014. This is the same year as my article, Turton, I believe it is, yes, same, or maybe the year before. Anyway, so they tried to take advantage of this. And so remember, I dropped the N1, but they didn't, we used the RZIF is the full nonlinear term. It's the exact U bar that we're using. But here, this is not. This is replacing this by only the first contribution. So this system is closed. This is a system in U bar and U1. Now, the big thing that I did there is they'd solved for U bar with Newton's method, and then they solved a diagonalization for this system, and they had so much trouble. They have a whole, the physical letter just does it, but then the physical fluids describes all their numerical problems doing this and getting this to converge, and they had to add a relaxation factor and this and that. So nobody should do that. It's much better to just solve with a single couple problem with Newton's method. I don't know why they didn't realize how possible it was to do that.
It's a simple quasi-linear system, isn't it? With one fluctuation.
It is, that's right. But they didn't have, I guess they didn't have the tools or think of it. They thought of this as intrinsically a Newton problem and intrinsically an eigenvalue problem.
Right.
Somehow. And so they introduced, they had to introduce an amplitude A, because after all, this doesn't, this doesn't determine the amplitude of U1 if it's an eigenvalue problem, if you don't do it coupled. So they then had to vary the A, and then they had a chart of sigma as a function of A. They decided the right sigma was when A was when sigma was equal to 0, and then they went back. Anyway, it took forever to describe anyway, and we just did it full Newton. Now I have to say our thermosolution problem is very small, so I can't really boast about that. But I do think they could have done it full Newton if they used matrix-free methods. But forget that. It was a great thing that they did, because look what they have. This is a field. This is direct numerical simulation, and this is the SCM. SCM stands for self-consistent model. And although, yeah, they didn't put the N here, and so you see it's perfect matching. It looks really nice. And of course, the thing, what is all this? Oh, this is them writing there more about it. And here's what we really want to see is the match. This is SCM and RZIF and exact. So great, they've done it with just the U1. So they're better than RZIF. Not only do they have agreement, but they also have agreement with just a U1. And this is this bad linearization about the base flow. All this is cylinder wave. Remember, I told you that my novelty is using thermosolutal as an example and not this. Okay, so that's great. So now we know RZIF is true, SCM is true, except. Let's go back to thermosolutal problem. Everybody remembers thermosolutal problem. Everybody remembers traveling waves satisfy RZIF, standing waves doesn't. So let's work on the traveling waves. Why wouldn't we work on the standing waves for this? Just trying to see if you're paying attention. If you can't even get it to work with an exact mean flow, how on earth are you going to get better by using an approximate mean flow? Okay, so of course you can't. If it doesn't work for RZIF, it certainly isn't going to work for SCM. SCM is an approximation on RZIF. Okay, so we're only going to do it with the traveling waves, which works so well for RZIF. And basically, I have just one slide here for this part, which is to say, okay, this is a slide we've been seeing all this time. This is omega. The exact traveling wave frequency is black here, and if we do RZIF, we get the red, and then if we do SCM, we get the green. So RZIF works, but if you try and make an approximate mean field constructed just by your U1 and your U1 star, no, you won't get it. Remember that what you did for the RZIF is you neglected the U2. But apparently, okay, as in terms like U2 and U1, we neglected that because that was in part of N1, right? We neglected this part. That was part of N1. 2 minus 1 is 1, so that was N1. But RZIF has a full mean flow, so it has terms like 2 and minus 2. 2 minus 2 makes 0, so it contributes to the mean flow. So we can't just drop U2, say bye-bye U2. We need this term here, it would seem. We didn't need it here, but we need it here. So it's not enough to say drop this mode. You have to say drop this mode in this interaction, it would seem. Let's see what I have next. Yes, so SCM, because people were happy with SCM, they went on and tried to do higher order SCM, where notice that these equations, they have everything. If you drop U2, this is just a very truncated system. You drop U2 every place, and 3, 4, 5. Okay, you say, all right, it doesn't work. Let me include U2. No, it doesn't work. Let me include U3. Doesn't work. Let me include U4. You could increase that way. And so we did that too. And we get, this is the one you've been seeing. Then it gets slightly better. Here, this is the green that you're trying to get. It gets slightly better, and then eventually gets better. But you know, how would you know if you didn't do the whole problem before? And that's the whole problem. If you want to do something that's going to save you time, you don't want to do the whole problem first to see if your time-saving thing works. You need to know why and when it works. Yes.
So basically, if you have like a global frequency, which is very different from everything else, then the SCM is going to work because one mode is enough. But if this mean flow itself has all the frequencies, it's not going to work.
If the mean flow has contributions, yes, from the other ones,
Yeah.
it's not going to work. That's right.
So like whenever you have a dominant global frequency, like in a Carmen street, it's going to work.
So you think you know, because that would be very, you think you know how, why that's, okay, really, I'm telling you pretty much everything I know. And if you have other ideas, I mean, more things will come along here, but not much. So you can see there's still plenty of to answer. So, you know, thoughts are welcome to explain why and when.
Can I just ask a question about this? You were saying that you didn't know when you were right,
Yeah,
but presumably there's also a growth rate that you're predicting too?
there is, but in SCM,
Yeah.
you define it by growth rate equals 0. Unlike RZIF, that's a very good question here. You recall that here, because you're determining this one, yes, you put in for SCM, you put in that sigma is equal to 0.
You do that, you just time step the equations. The quasi-linear equations, you just time step them. I don't know why they've done this post.
Well, we can talk about it. We can talk about it because they're not. I mean, I'm saying they should have done a better thing numerically, but I don't think they made a conceptual mistake. But we can talk about it.
There's another paper like this in convection by Daniel Lecone doing the same sort of thing.
Okay.
I don't know why they do it. But
We'll
we can talk about it. Yeah.
yeah, we'll talk about it. Do I have that in my list here of? No, I still have just that. Okay. Yeah. Okay. So we can talk about it. And that's when that's higher SCM. And then I think I've told you most. Okay. So we decided to try and find other counterexamples. I should have said it from the beginning. Okay. The work. The RZIF work was done by Sam Turton, who was a Cambridge undergraduate who came to me for a summer project. And the other work with the one showing that SCM didn't work, this was done by Yassine Begana, who was my PhD student, who's now postdoc with Young Imperial. So he really wanted to find another counterexample. He said he wanted to find an exclusively hydrodynamic one where you didn't have a field like a temperature field. So we wondered, Stefan Fauve say, did he have any ideas? And I should have realized, because I know Taylor-Couette flow, this which was just telling me. Here's counter-rotating Taylor-Couette flow. This is like the other slide that I showed you. Everybody knows Taylor-Couette flow. Okay, here is the map of Taylor-Couette flow.
How did you get that in color?
How did I get them in color? The 20 guys colorized it, and we'll give it out for free. I'll give it to you. Isn't it nice? Yeah. Once we played at the Taylor-Couette conference, we call it kind of a drinking game or bingo game. How many times are we going to see this this picture? You know, ding, we saw it. So in counterweight, everybody knows in either just the inner cylinder rotating or co-rotating, you have axisymmetrics for steady solutions and wavy ones. But in the counter-rotating case, you have spirals. In this region here, you have spirals, and this was discovered again in the glorious 80s of the dynamical systems. This was Golubinsky and Langford that said, oh, wait a minute, if you have spirals, then you have them this way, you can have them that way, then you can have a superposition. It's exactly analogous to the standing waves, traveling waves of Knobloch for the general case. So here you have simultaneously forms. And the experimentalists there in Swinnyland had a very hard time producing the ribbons, it's called, because all these things say there exists, but they don't say how stable they are, how much, what parameter range and so on. But anyway, they were found. So here are spirals, of both kinds, and then you superpose them and you get ribbons. So that's like standing wave travel waves. So Yassin was hoping that we would have RZIF for the spirals, but not for the ribbons, because they look like the standing waves. But lo and behold, oh no, this is the bifurcation diagram here, the two of them. Hold on. Oh, yeah, sorry. This is the ribbons, and this is and then this is the excuse me, this is the spirals, this is the ribbons. I wish I don't know how to make all the movies go at once. Anyway, here they are. So that's ribbons, and that's ribbons are on the bottom, and spirals are on the top. And these are the mean flows. And again, spirals are traveling wave solutions, so not necessarily there's no dependence on theta or on Z. But the mean flow for ribbons, it has a dependence, just as Sergey said, not necessarily because it's not the same. But then this was the disappointment. The omega, it works just the spirals and the ribbons have different frequencies, but you linearize about their respective mean flows and you can get the right answer for both. Here is the RZIF about the ribbons, and here's the RZIF in the spirals. So it works for both of them. So Yassin was disappointed at not having another counterexample.
You look at the frequencies, do you see separation?
Well, you see the frequencies here, right? They are different here and here for the ribbons and for the spirals. Spirals have this frequency and the ribbons have this frequency. I believe we did that too, but I don't think I have that. I don't think I have that. Yes, I mean, it's in the paper, but it's not in the slide. Okay, so an important point though, is that these, I mean, I said that these are obviously traveling waves, right? But these, you don't see them so obviously as standing waves. They look as though they travel, right? And that's because there's both Z and theta. As far as if you do a plane here, this is a plane with a single, sorry, I'm not so good at manipulating. Here, no, I want my movies. Come on. This one. Yeah, okay, this is obviously this is at a single theta. And you see traveling wave in Z. And here in this movie, at a single theta, it's a standing wave in Z, but you see that it's a traveling wave in theta. So it's not completely a standing wave. So you can't really say, oh, here's another case where you have standing wave travel. It's analogous, but it's not really the same case. But so far, so we didn't succeed in finding another counterexample. We then tried yet another problem. And so this is good because we generated paper after paper about different things. This is the shear-driven cavity here, and turns there's two solutions. This bifurcation diagram. They're both Hobbs bifurcations. Basically, they're little tiny brown cells that go around and around, and you can't count too well. But there's 4 little cells, hence like it's not exactly periodic, but so we put 2, and this is 6 little cells. There's like yellow, green, as you can call it, 3. And so anyway, they both have the RZIF property. The RZIF property being that black equals the circles, the black. Anyway, these match here, and these match here, and this is 0, and this is 0. So both the limit cycle 2 and limit cycle 3 have the RZIF property. So we still don't have any other counterexamples to RZIF, alone SCM. I don't think anybody else is in the counterexample business besides me. I was going to put in a little bit about resolvent analysis, because I thought I wouldn't have that much to say. I guess I can, but let me just do this really quickly. You can see I don't have much to say, there's just 3 slides. We all remember this equation, I omega U1 equals L U1 plus N1, and we remember that we dropped N1 to make it a linear equation with the eigenvalue here. Remember that, right? Okay, so McKeon and Sharma, this is what, I mean, we heard a lot about it at the workshop, but this is really kind of stepping back and introducing what this is. Let's leave the N1 in, and let's not even assume anything about it. Let's not assume anything like, let's not truncate it. Let's just leave, here's N1. Let's just invert this here for U1. Oh, I'm sorry. Thank you. Let's just leave the N1. We're not going to drop it. We're not going to approximate it. We're just going to leave it. And then we just rearrange things so that we have U1 equals I omega minus L bar U. This is linearization about a mean flow. What kind of mean I haven't said. And we just give this a definition. This is the definition of this. This is called the resolvent operator for a certain omega. So that's the definition here for any n. Now, you could write this also for any omega. So you could, in fact, apply this to, say, turbulent flow, which has a spectrum. So you don't have to have, I had I omega, 2 I omega, 3 I omega, but this could just be omega, a continuous omega. You could just, I mean, everything I've said here is completely general. It's just that this N1, I mean, the true N1 in Navier-Stokes is U dot grad U minus U bar dot grad, not minus bar, no. It's U tilde dot grad U tilde bar minus U bar dot grad U bar. It's the nonlinear interaction between the that contributes to the mean, but not, that doesn't contribute to the mean, right? The nonlinear interactions that don't, okay. But here, if you act as though it's some guy that you don't know, because how are you ever going to go? You barely know you. How are you going to know U tilde that grad U tilde and U tilde that grad U tilde minus a bar minus, you know, you're never going to know that. So you might as well treat it as an unknown. Now, the next step, so let's continue to forget this n. We write this, we do a singular value decomposition on R. So that is, we get modes R phi j equals mu j psi j. That's just singular. And now I'm not talking about n, I'm only talking about the R, just doing, it might as well be an eigenvalue decomposition, but it's singular value. It's better apparently in these circumstances. Now, and this is what we had, that's why I was so quick to jump on this when we were at the conference last week. Suppose that all of these are really small compared to one of them. Then what does this do? As far as space is concerned, say it's mu1 or mu dominant, I call it here. And what you're doing here is you're projecting on psi dominant. That's always what you can find. No matter what you're acting on, no matter what you act on, or no matter what the n is, you will always get this because the other contributions are so small. It's really just projecting n, and hence this lack of importance of what is n. Oh, is it supposed to be U tilde that grad U tilde? And I don't know what U tilde is. And you just say it's of this form. So that's nice. Here, it's of this form, but you need more than form. You would like an amplitude. Well, the amplitude you find by fitting. So here, I write this here. Maybe you fit the correspondence between U and you have your psi from your resolvent, and you also have your U, your spectrum, and you determine you don't. That's the part that's not quite so, that's going to be different for each case. And how do you find your mean? Well, that you put an experimental probe. You have much more chance of finding a mean than finding the whole spectrum for all omegas. But here's an illustration of the point that McKeon and Sharma were saying. The first one, this is logarithmic, is much bigger than the other ones. So we might as well just consider the big one and just consider everything to be projection onto psi. So we have the shape, and this depends on the omega. So this is going to give you the spectrum. The spectrum is this scalar amplitude. So that's kind of distinct from the RZIF SCM story, but it's a little bit like it. So I wanted to put that in. If what we did last week was very dependent on knowing all this already. But so I put in a kind of retrospective introduction to the resolvent analysis that's done by McKeon and Denise Game, and it's a whole. At one point I thought I should put lots of names so that people would find themselves, because everybody likes to find them, but I didn't have time to do that. Anyway, so this is resolvent analysis. Is not dropping the N1, nor assuming it's anything special about it, but considering it as arbitrary. Considering it as arbitrary and saying that all you want to do is project onto the largest sum. And you may wonder what the relationship is between RZIF and SCM and these other initials, QL and GQL, quasi-linear, general quasi-linear, and it's neither of those. You might think it would. So let me explain what is quasi-linear, general quasi-linear. You divide the modes into two categories. One is low, or you could say the mean, as we had, and the other one is high. It could be high spatial or temporal or high temporal. Anyway, you just say low and high. And these are the ones that you, and this is a procedure that does take into account dropping interactions, not merely modes. So that could be approachable. And here's what you keep for these. You retain the low, low. You retain the low, high, which makes the equations for the high linear in high, because you drop the high, high, except you keep the high, high, which generate the low, as in 1 minus 1 equals 0, 2 minus 2 equals 0, 3 minus 3. So those you keep, but you do not keep the 4 minus 3 is 1. So it's a lot like it, but neither of these methods that I've talked about are those. RZIF isn't, because it's not a closed system. You need the full mean, as we said, and you really do need the full mean. And SCM is neither, because it includes all the, once you decided to include, say, U2, you include it everywhere. So SCM is just a truncation. It's not, it doesn't, so it doesn't, yeah, SCM is not one of these either. So anyway, I wrote a paper about it. You can look it up. It's not very, very deep. So basically, this is my conclusion here. Linearizing about, we have limit cycles. If you linearize about the base flow, you're not going to get the frequency. Well, you kind of will for the driven cavity, because driven cavity is so simple that it really is like the hub one. Supposing you linearize about the mean flow, that's called RZIF. It works for the cylinder wake, it works for the thermosolutable traveling waves, it doesn't work for the thermosolutable standing waves, and it works for counter-rotating tailor-couette and driven cavity. And now we try something, another approximation. You approximate the base flow, so that's SCM, and that works for the cylinder wake. You saw all those things that the Kelly's group got there. And it doesn't work for either of this thermosolutable case, obviously not for standing waves, but not for traveling waves either. And I'm sorry I went over, and I'm sorry I had problems with my mouse. There, thank you.
Right. Questions?
Check the,
Chat.
I've got a question for you. Oh, that, who's that, Beverly?
Oh, yeah, that is Beverly.
Oh, hands up, Beverly. Go for it, Beverly. Can you hear me?
Hello, sorry I can't be there in person. Thank you, Laurette. You know I'm a fan of how you
Can you write your question, maybe?
Can you hear me?
Beverly, can you hear us?
One
Yes.
for yes, two for no.
So was it ever on Zoom? Because we don't see the Zoom controls. We usually.
Let's try that. No, we don't, do we?
Can you hear me?
Yes, I can hear you fine, she says. Can you talk to us, Beverly?
Well, I've been trying.
Can you write your question in the chat? I'm trying. Okay, so we'll wait.
I can answer my question while she's doing that, and that is, this, you know, this all seems, all the thinking seems tied up with weakly nonlinear analysis, right? And of course, the feedback is either the mean flow or the second harmonic,
Yes.
right? And you're looking at the case with the second harmonic doesn't really contribute, so it's all me.
Wait, I'm sorry, excuse me. I call you one, I call you one here, the first harmonic, and then I call you two,
Yeah.
second harmonic, okay?
So if I do weakly nonlinear analysis
Yes.
in terms of what happens to the primary,
Yes,
is there interaction? It's a feedback of the second harmonic and me, the third order.
yes, and without the one.
And basically, you're arguing that everything is in me, the mean contribution. You want to neglect the second harmonic.
So it seems, yes,
So what about if we look at?
except insofar as it contributes to the need, but, yeah, okay.
So let's take the opposite scenario where everything's in the second harmonic and there's no change in the mean.
Uh-huh,
So we contribute. Then the and the base flow are going to be basically the same.
yes,
So it should still work.
I would need more time to, I don't
But I guess
process
what I'm
this.
trying to say is in a way it's not going to work if they contribute equally. Because then the harmonic is just, the second harmonic is just as important as the mean flow correction. So actually, I think it's going to be quite hard to find. So if one dominates all the other, I think it's going to work. Because even, you've got this RZIF.
RZIF,
RZIF. In the other scenario, the mean is the same as the basic flow.
yes. What, wait, the other scenario, you mean the SCM?
No, the
No,
other scenario
no.
where basically the mean and base flow are the same as the other.
Okay, so we didn't show any such
Yeah,
things, right?
yeah. So I think the only way it's not going to work is if they both contribute roughly the same magnitude. So you get a change in the mean and also the second harmonic is significant.
Okay, we'll discuss, as I said.
Yeah.
Oh, but one thing I've learned in all this, there is a word for the change, mean minus base is called the distortion. So,
Yeah,
it's gotta be
mean flow change. Yeah.
there.
Okay. Oh, she's got a question.
No, it's not there yet, I don't think. Oh, yes, it is.
That's a long
Yes, it is.
question.
It's a long question, yes.
You get on the board.
Okay, so it says, George, you're talking hydro commonality differences between projects. A minor correction would resolve analysis. In the absence of other information, one resorts to the first mode in the presence of large sigma separation. But we wrote out the full expression several times, and it was used by several speakers last week.
So could you just correct it? Any questions? Yeah, Daniel, go ahead.
I wonder if you can clarify again the difference between SCM and the quasi-linear.
Yeah,
What was the thing of the steps?
right, okay, hold on. Okay, yeah. Thanks, Beverly, and yes, some other person has also corrected, she said, I like how Laurette auto-corrected to Laurette, which I've seen before, so. I have a Laurel wreath, okay, so hold on, oh, is this is not gonna let me, okay. They're going to go back to. Right,
Screen it, no.
yeah, okay, I'm not, is it?
Yeah, not on
Oh, I know why, yes, okay, I'll, hold on just a second, do a share again, on. Wait. Desktop. And this is here, that's fine. And now I want to go here, okay,
Not saying yes, no,
Oh.
but the participants can see it.
is that so?
That's what it just said.
Oh, hold on, just a second, stop share, I'll do what we did before. Just a second. Share screen, we do desktop too. Do that. There, now is it, no, still not? Oh, here, play. There, okay, right, okay, so, so the question was, why is this not, quasi-linear? Right, I think this is quasi-linear, very degenerate. But the prescription, what they call SCM2, is to add, yes, the prescription for, let's see. I mentioned that there was, yes, higher order SCM, and a couple people have published papers about that where you indicated 2 and 3. The prescription for SCM2 is to add,
Oh, do you add this?
Is it just the N one minus one? Is that the only term that's different? Because I didn't realize it was chopped up in the previous.
I'm sorry, what should I go back to? Should I?
That original slide where you had slash.
Yes,
yes,
yes.
That's it.
Yeah, so I didn't realize you crossed the, yeah, I didn't know that
Yeah.
one.
Well, this one.
This one
Yeah, I
here.
didn't, so.
No, that's
Yeah,
replaced by that.
crossed.
No, this is kept.
Oh,
No,
that's.
you
yeah.
you are right,
Yeah.
that SC, I believe, if I'm, it's wrong, that SCM is the same as quasi-linear here.
Okay,
But then if you decided to, but this is very truncated, this is just two, but this is just, generally when they do quasi-linear, then they have more. Yeah, this is how, right, the generalized quasi-linear does not mean adding more, adding U1, U2, U3, that's assumed. Quasi-linear would have had this, what we have here. I think quasi-linear in general would have this, and then U2 and U3 and so on. I believe, I'm not absolutely sure. That would be quasi-linear for with more than just U1. Generalized quasi-linear would have more guys that are like U bar. They would have U bar and a couple other guys here, and they would treat them like this. But yes, I think I agree with you. I'll have to check again that this is the very degenerate quasi-linear case. Yes.
How do they extend it when they add in that U2?
When they add U2, I think they extend it in just this way. Just LU, U2, U3, and so on.
And then they add the contribution to the mean.
And then they add the contribution to the mean.
That's quasi-linear.
That's quasi-linear. That's right.
So the question.
But oh, you're talking about you're talking about quasi-linear? Because I agree, that's quasi-linear. No, the SCM guys, what they do.
Yeah.
Okay, I'm sorry. So that's quasi-linear. I agree. The SCM, when they want to extend it, they but I mean, they don't have to. This is just a definition they made. They add they will add U2, say everywhere it appears. They'll just have U3, no U3, and they'll have U2 here, and they'll have U2 here. But no, okay.
Is the equation for U2 linear too?
I think it necessarily is. Yes, it is. It is. It will be.
So then it'd be quasi-linear. Or do they have the
No, the linear things in there.
Oh, it's been a while since I thought about this.
The linear part, and then they have the N1,
That's the
linear thing, but we don't know you see.
Yeah, but this is just Navier-Stokes, isn't it?
Yes, but they've never done SCM. I mean, SCM is all
No, but in terms of when they extend SCM,
Yes,
how do they fit in U2? They certainly put it into the mean equation.
they put it in every place where it is. They just have U3 equals 0.
Oh, so then they put U2 and U1 minus 1 interacting in the U1 equation.
That's right. That's
So
right.
it's
They
just
have
like a
2 minus,
truncated.
that's right. It's 2 minus 1 equals 1, but 2 minus 1 equals 3, they don't have that.
Right, so it's a truncated Navier-Stokes.
Exactly, it's truncated
Oh.
Navier-Stokes. I believe SCM is merely truncated Navier-Stokes,
Oh.
whereas quasi-linear
Yeah.
is slightly different.
Okay, very good. Yeah, there we go.
Did I understand right that RZIF works when there's an invited separation?
I don't think I examined it that way. I examined RZIF works when your spectrum, the spectrum of your nonlinear limit cycle is mostly in the 0 and the first harmonic. If you go on to second harmonic, third harmonic, it's not. Let me see if I get that. There, this is a spectrum. So this is not like the, I don't think this is like the Zong thing. This is a Fourier temporal spectrum of the nonlinear limit cycle. And you can see that it's highly peaked for the traveling wave here. You capture most of your, and much less peaked than standing. So, but it's a Fourier transform of a nonlinear. So I don't, not thinking it is nonlinear. Is that clear?
And isn't why?
Why does that work? Oh, makes sense. It means, don't, it's because of, it's because of, this, that N1 is made up of, the terms that are like 2 minus 1 is 1, and that's of order, that's cubic order. So if 2 is really much smaller than 1, then you can get rid of this. And if 2 and 1 are kind of the same size, you can't. I mean, that's the way I was thinking of it,
Yeah,
but these
That's the
people
same-
had
that's the same as the weekly
interesting
nonlinear
things to
analysis approach, yeah.
say there.
Nice if someone can give a small tutorial on quasi-linear and generalized quasi.
Well, that would be Steve Davis, who,
Yeah,
who's,
yeah.
That might be very.
he's here virtually. I mean, he's listed as a,
Yeah,
and
yeah,
he will be here, I think, not just virtually at the last workshop.
yeah, definitely. Okay, any questions? Well, thanks. thanks a lot,
Okay.
thanks.
Oh, wait, I'm sorry.
Oh, there's another
There's
question.
another question. It's from, yeah, hold on, let's open the chat. No, it's from Ivan.
Ivan.
Hi, can you hear me?
Yes, Ivan, can you write your question in the chat?
Okay.
Is SCM types that similar to using triple decomposition method of Reynolds, and people saying, I don't know enough about triple decomposition method. Rich says no.
No. No. Very good. Okay, thank you very much. Thanks a lot.